All right, let's talk logarithms. That's not something you hear every day. Imagine just going up to a party and being, hey, let's talk about logarithms. Well, we're not in a party, we're in a math class, so which can be a bit of a party if you're having fun, so hopefully you are. When we looked at differentiating log functions, we saw that they became a specific type of function. The derivative of ln of x with base e just becomes 1 on x, right? So naturally, when we think about integrating, it's the reverse process. So there is some intuition that, oh, if I take the integral of the primitive, it just becomes log of x, right? But I want to unpack that a little bit, right? Because before, when we looked at our normal derivative rules, for example, integrate x squared, we added 1 to the power, and when we divided by the new power, and add your constant. And then I gave you ones that looked like this, so 1 on x, and thinking, well, let's see if I can try the same thing. If I write this in index notation, so -1, and I try that same rule, you get something that doesn't really quite work, because if you add 1 to this power, you get 0, divided by the new power becomes 0, right? So that doesn't really work here, okay? So over here, this is how we can actually integrate this kind of function. What is this function? This is a hyperbolic kind of function, right? So if I draw this out, there's some intuition why there should be an integral for this, right? Because if I draw out a hyperbola, there should be area under the curvature of 5, because that's something closely related to integrals, remember, right? And if I went from like 1 to some value like 2, right, there is some area that I should be able to evaluate there, okay? So this is our definition we want to use. This is what gives us our integral for involving logarithmic functions. So it's important to note we're not integrating the log, right? We don't have any identities for that in this course, but I'm integrating this function, and it involves a log because when I take the integral of 1 on x, right, I get my log of x plus your constant. So you can jot that down for me. That's our rule for this. But there's a disclaimer I need to make about this, and it relates to what you're actually integrating. You're integrating this hyperbolic function, right? And I'm saying when you do that, you're going to get a logarithmic function. There's a problem though. Now I wonder if you can pause and just have a think about what that might be. It's the fact that if you sketch your log function, remember, it looks like this, the basic one, right? This is y equals to 1 on x, this is y equals to ln of x. The issue is, I'm missing pretty much the whole left side here. And that's because a logarithmic graph is not defined for negative values of x, right? And think about how that's related to your powers and things like that. But this function is. So how do we kind of solve this problem? Because it seems like there's this disconnection here between when I have my derivative and I want to integrate to get the primitive. The solution to that is, well, we say x can only be a positive value, and we solve that by saying, okay, if x, we want to take the positive value of x here, we just add in these absolute values. So even if we want to check for x to be a negative number, we can substitute back in and we just get a positive value back in here, right? So that's the way that we need to write the integrals. They need to have these absolute values here, right? So let's look at a quick example. The way I'm going to approach these is I'm going to say, well, for example, if I want to find the integral of 2 on x, I'm going to look for where can I see 1 on x here. And then when I can do that, I can just straight up write it as the log of x. So when I'm looking at this, I'm like thinking, well, 2 on x. Another way I could write that is I can just say that that's the integral of 2 times 1 on x. Would you agree? Because this is just 2 times 1 on x. You put it back together, you get 2 on x. And anytime with constants, you can actually bring those out. And so you can see once you have it in this form, hey, I'm just looking for the integral of 1 on x. I can straight up put it in over here, right? So that's just going to be 2 ln of the absolute value of x, and then plus your constants. And remember, the constant we just kind of leave outside there because you could put it inside the brackets, but then you're multiplying by 2, and a constant, that just becomes another constant. So we don't need to really worry about that notation too much. Okay, what else can we do? These kind of questions. What about something like this? Same idea, right? So I've got now the integral of 4 on 5x, right? And again, I'm trying to rearrange this in such a way that I have 1 on x. And again, same idea, if you think about this, this is something you can kind of factorize out, because this could just be written as 4 over 5 times 1 on x. So I'm just going to pull it out there. 4 over 5 times 1 on x. And you see how these are the same now, right? Same ideas over here. If I put these back together, it's the same expression. And so when I integrate, I'm going to get ln of the absolute value of x plus my constant there. Right? All right, now similar to the exponentials, we have kind of like different forms that we can actually integrate, right? And the common form that we're going to deal with is this one here. So if I want to integrate 1 on ax plus b with respect to x, that's actually going to be 1 on a ln of ax plus b. Remember there's absolute values as well, and then plus any constants. Yeah. So this is my kind of more general logarithmic form for anytime I've got like a linear expression on the denominator there. So same idea, right? And the reason why is similar to with the exponentials, we're trying to account for the fact that when we differentiate this function over here, we have to involve the derivatives of what's inside. So to undo that, we're going to divide by a. That's the idea with this. And so if I'm ever given a function now of that form, so the integral of 1 on 4x plus 2, for example, right? Notice how in this one we've got an a value of 4 and a b value of 2. So I'm going to integrate this. And I can write the integral as, okay, well my a value is 4, so I can say it's 1 on 4 ln of 4x plus 2, and then we add on any constants there as well, okay? And we can try another one for good measure. So if I take, for example, integral of 2 on minus 3x plus 2. So I want to look at the integral of this expression. Again, I can see if there's anything I can factorize out to make my life a bit easier. And I can take out this expression over here. So I have a 1 on the numerator. So that's going to be 2 outside of 1 over negative 3x plus 2. And then you can just go ahead and identify your a and b values. So I've got a as negative 3, b as 2 here in this case. So that would be 2 ln, 2 multiplied by 1 on negative 3, ln of minus 3x plus 2, plus any constants. And so it would just be negative 2 on 3 minus 3x plus 2. Okay, all right. So that's kind of indefinite integrals using this form over here.